Look at that! These gentle beings have been like this for thousands of millennia, without a single change. Of course, I'm talking about beams of light!
The nature of light!
Welcome to The Nature of Light. I'm your host, Matt Allard, and in the course of the next period of time that this documentary goes for, I will be speaking to many famous physicists who've contributed to the current theory surrounding the nature of light. First, we will be speaking to Sir Isaac Newton. You've been referred to as revolutionizing the modern theory on light. Indeed, many physicists of my day considered my ideas to be revolutionary. However, there were many physicists at the time who had theories more accurate to what is commonly believed today. However, my influence in scientific circles made my ideas more widely accepted than many of the other more accurate scientists. My theory revolved mostly around a corpuscular theory of light, practically implementing a particle theory of light. Ah yes, photons. Yes. For example, my corpuscular model unfortunately depicted that light would accelerate towards a denser medium. In 1672, when I learned of Newton's corpuscular theory of light, I made sure to criticize it as fast as possible. That, and his theories on color. What did you work on then? I worked on theorems of double refraction and the velocity of light. This finally paying off when I completed my Traité de la Lumière, which argued my wave theory of light. But your theory had one unexplainable flaw. Ether. But ether was able to explain such a large portion of the reflection and refraction of light, despite it being a flaw. It's as I've always said, the nature of light is subject to no material importance to the concerns of life, but in many other aspects, it is extremely interesting. Your experiments were among what greatly strengthened the wave theory on light, am I correct? That's right. My greatest achievement was my famous double-slit experiment. If I'm not mistaken, this was a tremendous help in backing up Huygens' theory that light was made up of a series of wavefronts. That's right. The closer the slits are, the wider and the brighter the bright patches are. As they get further apart, the bright patches become thinner and in greater quantity. So far, it seems as if nothing has been decided on yet for an absolute dictatorship over which model is right. However, the double-slit experiment did give us some confusion as to what way light travels at all, due to its double nature in this experiment. Father was an architect, so I came from an engineering background, and I showed a keen interest in... Look, we didn't ask for your life story. But I worked for Napoleon himself. Just get on with what you actually achieved. Oh, of course. I was one of the few in favour of the wave theory of light. Unaware of the work of many other scientists, I came to a conclusion of my own. What was it exactly that you did, though? Basically, what I did was attach a piece of black paper to the diffractor and noticed that the bright spots disappeared. Similar to Young's findings, I derived that elementary waves arise at every point along the arc of the wavefront passing the diffractor, and mutually interfere. The problem was to determine the resultant vibration caused by the wavelets reaching any point behind the diffractor. The mathematical difficulties were formidable, and the solution was to require months of effort. I see, and did you lead on anywhere from that? Well, after an award for that work, I was encouraged to go on and tackle the last hurdle opposing the wave theory of light, polarized light. Would you be able to explain this to me? Now that's impossible. Using my degree in mathematics, I made my contribution to the understanding of light using the extension of Faraday's concepts of electricity and magnetism. So how did this come into effect? Well, after discovering that the propagation of light must be equivalent to that of electricity, I expanded it further to be the velocity is so nearly that of light that we have strong reason to conclude that light is an electromagnetic disturbance in the form of waves propagated according to electromagnetic laws. I usually studied waves. After all, the unit of wave frequency was named after me. Yes, but what exactly did you lead on to from there? Developing Maxwell's theories, I experimentally proved some aspects of his work. I see, but how did you operationalize this?
I set up a condenser consisting of two oppositely charged metal rods with a gap between for a spark.
Okay, what did you do then?
Timing the waves, I demonstrated that Maxwell's theory that electromagnetic waves and light have the same speed.
Was there anything else you actually discovered?
The photoelectric effect, but it makes no sense to me.
So how did you get started in the industry?
As an assistant to Heinrich Hertz, I worked and shared many scientific interests with him. In 1888, I began working on cathode rays, and in cooperation with Hertz, compared their behavior to that of UV rays. And in later work, I was able to separate cathode rays into conventional cathode rays using aluminium foil and Hertz's ideas. After my colleague's death, I extended his work into the photoelectric effect. Can we show a diagram?
Let's take a look at that diagram, shall we?
Decreasing the frequency makes the light closer to a blue wavelength. As noticeable up the top, the current of the circuit is increasing as the wavelength decreases. Now in the invisible ultraviolet spectrum, the current of the photoelectric effect continues to increase. Increasing the light intensity can both increase dramatically or decrease dramatically the current of the circuit.
Basically, what else I discovered is that the electrons fired off using the UV light could also be directed using magnetic fields in a vacuum.
Though Leonard's findings weren't actually in line with current beliefs, they really came into their own when Einstein's findings showed them to be much more useful.
If you think you can get away with not subscribing to Carpe Clunes, think again.